Solution for heteroscedastic disturbance. When the heteroscedasticity is established on the basis of any test, the appropriate solution is to transfer the original model in such a way as to obtain a form in which the transform disturbance term has constant variance. We then apply CLS, classical least square, the transform model. Then the transformations of the model depends on the particular form of heteroscedasticity. Sigma ui square is equal to f of xi. So the transformations of the model depends on the particular form of heteroscedasticity, that is sigma ui square is equal to f of xi. Case 1, it's suppose heteroscedasticity is the form of expected value of ui square is equal to sigma ui square is equal to k square x square. The appropriate transformations of the original model consist of the divisions of the original relationship by root x square is equal to x, or x square root of x square is equal to x, which means that the appropriate transformation version is yi is equal to alpha plus beta xi plus ui. If we divided both side by xi, we get yi divided by xi is equal to alpha divided by xi plus beta xi divided by xi plus ui divided by xi. So expected value of ui divided by xi square is equal to expected value of ui xi square is equal to, from this line we are taking expectation and divided by xi, and so we get the k square, this term is cancel out and then get k square is constant. We now random term is constant variance, we may apply classical least square to the transform model, and the case 2 assume the form of heteroscedasticity to be expected value of ui square is equal to sigma ui square k square x. The appropriate transformations of the original model consist of the divisions of the original model by root x, that is y it's divided by root x is equal to alpha divided by root x plus beta xi divided by root x plus u root x. Expected value of ui divided by root x square is equal to expected value of ui square divided by x is equal to k square into x divided by x. It's ultimately get a constant term, that is k square. So non-spherical model heteroscedasticity and 0, in the non-spherical model heteroscedasticity problem is there, but 0 autocorrelation. Consider two variable linear regression model y is equal to x beta plus u, expected value of u it's equal to 0, and the expected value of u transpose is equal to the variance term are non-constant but covariance terms are 0, because there is no problem of autocorrelation but only problem of heteroscedasticity. So it's equal to sigma u square omega. If sigma u square is equal to 1, then only omega into 1. So omega inverse is equal to 1 by sigma 1 square, all the values are 0, 0, 1 by sigma u square, and other terms are 0, and the last row there is the last column value, it's 1 by sigma n square. So direct GLS estimation yields that it's equal to beta hat GLS is equal to x transpose omega inverse x whole inverse x transpose omega inverse y. So direct GLS is too much cumbersome, so we use 2SLS techniques, and omega inverse is equal to we already mentioned the value of omega inverse, and 2SLS technique. In the first stage, we transform the non-spherical model to spherical model by using transformation matrix rho, and rho transpose rho it's equal to omega inverse. And in the second stage we use classical least square technique to estimate the parameter of the transform model in case of heteroscedastic with no autocorrelation. model, the row matrix is rho is equal to 1 by sigma 1 and other terms are 0. In the second row 0 1 by rho 2 and other rest of the columns are 0, and in the last row only the last column value is 1 by rho square. It is actually a square root of the reciprocal of omega matrix. So rho inverse rho, it's multiply rho inverse rho and get omega inverse. So in the from here x star beta, it's equal to rho x beta, rho matrix beta x and beta. If we multiply n cross n matrix and n cross k plus 1 matrix, then we get 1 by sigma 1 x11 by sigma 1 up to xk1 by sigma 1. In the last row, that is 1 by rho n x1n by rho n up to the last column, it's xkn divided by rho n, and the beta matrix is beta naught, beta 1, beta 2 up to beta k. If we multiply n cross k plus 1 matrix and k plus 1 cross 1 matrix, the last beta matrix, then we get beta naught divided by omega sigma 1 plus beta 1 x11 divided by omega sigma 1 plus up to beta k x k1 divided by sigma 1. In the and in the last row the column values are, in the last row the value is beta beta 0 divided by sigma n plus beta 1 x1 n divided by sigma n plus up to beta k x k n divided by sigma n. This is n cross 1 matrix. Our new model ith equation will be written as yi divided by sigma I, it's equal to beta naught divided by sigma I plus beta 1 into x1 I divided by sigma I plus beta 2 x2 I divided by sigma I plus up to beta k x k I divided by sigma I plus ui divided by sigma I, where expected value of ui divided by sigma I, it's equal to expected value of ui divided by sigma I, it's equal to 0. So variance of ui divided by sigma I is equal to expected value of variance of ui square, that means expected value of ui means ui square divided by sigma I square, it's equal to expected value of ui square divided by sigma I square, it's equal to we know that the expected value of ui square equal to sigma I square, and in the denominator there is sigma I square, so sigma I square it's cancel out and get 1. Here the new model shows again spherical property. New model estimator gives beta naught hat divided by sigma 1, beta 2 hat divided beta 1, beta naught hat divided by sigma 1, beta 1 hat divided by sigma 1 up to beta k hat divided by sigma I or 1. We only get the estimated value of beta naught hat, beta 1 hat, beta 2 hat up to beta k hat, provided that sigma 1 square is given for the ith equation.